The goal of physics is to gain a deeper understanding of the world in which we live. To that end, physics is the study of the fundamental laws of nature. These laws can be expressed in terms of mathematical equations. To make quantitative comparisons between the laws of physics and our experience of the natural world, certain basic physical quantities must be measured. Those quantities, for us, are going to include mass, which is measured in kilograms, length, which is measured in meters, and time, which is measured in seconds. These quantities are based on standards that were developed over the years, and we'll use those as our measurement instruments. We also will make use of scientific notation. For instance, this number, which is called Boltzmann's constant, is got a lot of zeros in it. In order to make it more usable, we're going to put it into scientific notation. Makes it much more easy to manage. This number also, which is the speed of light squared, is something that we'll use from time to time. We'll put in scientific notation as well. Notice in the first one, because the zeros are all in front of the number, our exponent is negative. In the second one, because the zeros are after the number, our exponent is positive. Significant figures play a role in any type of measurements. The rules for significant figures can be confusing, but if you understand how to count the zeros, it makes a big difference. For instance, zeros between other non-zero digits are significant. In the number 606, there are 3 significant digits. The zero in between the 2 non-zero digits is a significant value. Zeros in front of non-zero digits are not significant. So the 3 zeros here are not significant. The only ones that are the 1 and the 2. So this would have 2 significant digits in it. Zeros that are at the end of a number and also to the right of the decimal are significant. Both things must be true in order for the zeros to count. 27.00 contains 4 significant digits because the zeros are at the end of the number and to the right of the decimal. Zeros at the end of a number and to the left of a decimal are significant. For instance, in this value, 1300, the 2 zeros are significant. So this value would contain 4 significant digits because the decimal place is there. When we calculate with significant figures, there are 2 different sets of rules that we must follow. One for addition and subtraction, and another one for multiplication and division. In addition or subtraction, the final answer should have the same number of digits to the right of the decimal as the measurement with the smallest number of digits to the right of the decimal. In multiplication or division, the final answer has the same number of significant digits as the measurement having the smallest number of significant digits. So in addition and subtraction, we count the numbers after the decimal. In multiplication and division, we count the numbers, period. Mathematical notation. There are some symbols that you're going to need to be familiar with as we go through this process. For instance, an infinity sign in physics means is proportional to. The squiggly equal means it's approximately equal. We're not sure that it's an exact measurement. We're close, but we're not sure. 3 lines means it's defined as. The triangle is the change in. Sigma is the sum of, and alpha is a standard deviation. We won't do a lot with standard deviation, but whenever you see a number that has a plus or minus sign after it, they're talking about the standard deviation of that value. Accuracy and precision is also something that we need to take into account in physics. For instance, if our values are not very close to each other, we've made 4 hits on the target, they're not very close to each other, they are neither accurate nor precise. Accuracy is defined as how close a measurement is to the accepted value. Precision is defined as how close together or how repeatable the results are. Since none of these are at the bullseye or are close together, they're neither accurate nor precise. In this example, the shots are precise because they're all clustered together, but they're not accurate. They're nowhere near where they should be. In this example, all 4 shots are now both precise and accurate. They're in a cluster together and they're on the bullseye. When we talk about errors, we have error analysis systems that will help us determine what type of error is going on. There are actually 3 types of errors that we need to be aware of. The first type of error is a personal error. It's mistakes made by the experimenter. This type of error can be eliminated completely by assuming things are going to go wrong unless careful attention is given to making sure that no mistakes are made. The second type is a systematic error. Systematic are errors that tend to be in the same direction for repeated measurements and usually involve the equipment. There's something out of alignment, something that hasn't been zeroed out or tailored, something wrong with the equipment that we're using, and so we repeatedly get the wrong measurement or the wrong value. The third type is called random error. Random error are things that we have no control over. Unpredictable, unknown variables that we can't do anything about, and we're never going to be able to completely eliminate them. When we talk about error analysis, we want to focus on systematic errors, those errors that are caused by something in the instrumentation or something in the measurement system that we're using. We have no control over the random errors, and we try to eliminate as many as we can think of. And we have control over the personal errors because we can make sure that what we're doing, as far as we know, is the best that we can do. Systematic errors tend to not be anything that we can do anything about, so we need to be aware of those as we're going through this process. For our first podcast, I chose to keep it very short and simple. These are the main points that you're going to need to know for this unit, specifically measurements, units, significant figures, and scientific notation. Once we have those things under our belt, we are ready to move on to the good stuff.